Let's consider how we would find the potential between 2 points A and B due to some point charge Q, which is located at the origin. So what we're going to want to do is we're going to want to utilize that integral equation from the previous video. So we had said that our VAB is equal to negative the integral from some point to some starting point to some ending point of E dot dl. So what we need to do first is we need to somehow identify the position of points A and B. And so of course what we can do is use position vectors. So we can say point A is identified in space by position vector RA, and point B is identified by some position vector R sub B. And so notice I've said my Q is at the origin, but of course we're going to generalize and see how it can be related just to distance from our point charge. So our limits on integration then become from RA to RB because we want the potential at B relative to A. Again, keeping in mind that this notation VAB is opposite of what we see in some of our other electrical engineering classes. All right, so we then know our expression for our electric field for a point charge is going to have radial symmetry from the point charge. So for example, if we were to sort of draw directions of our electric field, we would have directions of E sort of emanating with radial symmetry from this point charge. And so because of that, what we're going to see is that the only dl direction that's going to produce any work is going to be in our r direction. And so this sort of comes back to something we talked about earlier, but basically the path that we take between these 2 point charges isn't going to matter. So it's going to be independent, sorry, not between the 2 point charges, but between our 2 points A and B. So this is going to be independent of the path. And so we could look at any point along here and we could say, we have some dl. So this would be some differential length dl. And the only time that dot product is going to be non-zero is when we have the dl in the r direction. So writing that out, what we get is negative the integral from RA to RB of, now our electric field, as we found before, for a point charge is Q over 4 pi epsilon naught r squared unit vector in the r direction. So there's that radial symmetry that I was talking about with the green lines. And then we're going to dot that with dl. And so just based on our definition of the dot product, any components that are in the phi or the theta direction, if we do a dot product of that with this u of r here, it's going to go to 0. So what that means is the only component that is really relevant is our dr in our r direction. Okay, so what we get from that is we evaluate the integral. So essentially we just have this, so really I've not shown the full sort of vector here, but we do have some phi, we potentially have some phi and theta component depending on the path. But remember, ultimately this is going to be independent of our path such that only that r component, independent, well, excuse me while I try to spell independent correctly here. So independent, there we go. Okay, so it's independent of this path so that only that r direction is really what's making a difference. And so what that's telling us is if they were at the same distance from Q, then our potential would be 0. And so we'll see that in this equation we're about to write a little more clearly. So we would have then VAB, if we perform that integral with respect to r, so we're going to have our Q over 4 pi epsilon naught, which is essentially just a constant. So that just comes out, and then we have 1 over r. We also have a negative sign when we integrate, which is going to cancel out with this negative sign out front here. And when we evaluate at our limits, we have 1 over RB minus 1 over RA. And so this would be equal to VB minus VA. So notice this is the potential between the 2 points. So if we wanted potential at just the one, of course voltage is always referenced to some point. So we have to have 2 points to properly define a voltage. And so typically in electromagnetics, what we're going to do is define that reference point at infinity. So typically we will choose infinity as our reference. And so what we're doing then is we're saying at infinity, our potential is 0. So for example, if we said, let's let our A point be our reference point, so maybe instead of having this A right here, we made this point A infinity, so infinite distance away from our Q, then what we would have is our VA, because it's at infinity, is equal to 0. So our RA is, to be more correct, let's say it's going towards infinity. It's not at infinity. So as RA goes to infinity, that potential goes to 0. So what we can do then is we can simplify this potential difference equation, and we could say the potential at some point, so the potential at some point R, so position vector R, due to a point charge at the origin, is given by V equals Q over 4 pi epsilon naught R. And so essentially we can get that just by plugging in those values for VA equals 0 and RA going towards infinity into this equation up here, and we get this expression right here. Now, of course, we can define things locally as opposed to globally, so this doesn't necessarily have to be the distance R from the origin. Obviously, we can just say that's the distance R from our point charge of interest, and we'll see that in the next video. We can kind of scale that up for multiple point charges. So one thing to note is that this is a scalar quantity. So this is not a vector, there's no direction associated with it. And we can also talk about sort of this definition of the potential at a point a little more generally. And we can say this potential is equal to the work done per unit charge to bring a point charge from infinity to the point where we're evaluating the potential. So our R position vector in this case. So work done per unit charge to bring a test charge to R from infinity. And so again, not necessarily a crucial definition, but maybe just gives you some more insight into physically what we mean when we're talking about potential. So we're saying if we have the origin here, and here's our point of interest, so maybe this was point B, and this is our origin. And so we have some position vector, which is R, just to be consistent with our notation right here. So if we have that, then our potential VB is equal to the work to take a charge, a test charge, all the way over here at infinity. So obviously I can't draw this at infinity, but let's say that's infinity, to bring it from infinity to this point at B.